Hello, and welcome to the second video of the FP2 chapter Maclaurin and Taylor series. On the screen, a quick review. From our previous video, we had this as the Maclaurin series expansion for f of x. We also had a specific example of that, which was e to the x, and we found that that was this expansion for all x values. There are a few more that I'm going to quickly go through here on this screen. Natural log of 1 plus x expands to this with a general term here. You can see the pattern, x squared over 2, x cubed over 3, x to the r over r, and then we have a plus minus pattern, which we get using this here. Now this is valid only for minus 1 to 1. Sine of x, we had a few of these. We had these first 4 actually. We had the first 4, and then we used the first 2. And here you can see the general term. Again, we've got x to the odd number divided by an odd number factorial, and a minus 1 term to make sure that this keeps going alternate. And this is true for all x. Then cosine, which we didn't do in the previous video, is very similar. The general term, except for odd numbers changing to even numbers, is pretty much the same. So here we've got x squared over 2 factorial instead of x cubed over 3 factorial. And that also is true for all x. Finally, arctan or inverse tan is very similar to the sine function as well, except that instead of factorials, we've just got the numbers underneath here. And that's only true for minus 1 to 1 on your x values. So the starter question here is, which of these are given in your formula booklet? Because these would be very annoying to have to memorize. And the happy answer is all of them. You don't need to memorize any of these. They're all given to you in the formula booklet. A consequence of that is that the examiners can set questions based around these using compound functions, which is what we're going to look at in this video here. So we can find the Maclaurin series expansion for compound functions by substituting a different expression for x in the appropriate expansion formula, which you will either have figured out in the first part of the question or will be one of the expansion formulas given to you in the booklet. And in terms of notes, that's it for the whole video. We've got 3 examples to go through to show how this works in practice. The first one is write down the first 4 non-zero terms in the series expansion in ascending powers of x of cos 2x squared. So here we need to know the formula for cos x. This is in the formula booklet, written like this. So all we need to do here is, instead of writing x, write 2x squared. And then everywhere there's an x in the formula, replace that with a 2x squared in brackets. Be careful to put the brackets in, because when you do powers on this, it will affect the 2 as well as the x squared. So I'm just going to go through that here. I've got the 1, that doesn't change, minus, instead of x, 2x squared over 2 factorial, plus 2x to the power 4, 2x squared to the power 4 over 4 factorial, and then following the pattern, it will be 2x squared to the power 6 over 6 factorial. And these are the first 4 non-zero terms. Now in this sort of question, I need to simplify everything, including the factorials. So I'm going to put a little approximately equal to sign here, so I don't need to keep writing the plus dot dot dot, and then start simplifying. So we've got 1 minus 4x to the power 4 divided by 2 factorial, which is 2. So that simplifies to x power 4 with a 2 in front. Then we've got 2 to the power 4, which is 16, divided by 4 factorial, which is 24. So we've got 16x to the power 8 over 24. That, of course, I will simplify again. Then we've got minus 2 to the power 6, 1632, 64x to the 12, divided by 6 factorial, which is 720, and then I'll simplify that by putting it on my calculator. So our final answer is 1 minus 2x to the 4 plus 2x to the 8 over 3 minus 4x to the 12 over 45. Second example. Find the first three non-zero terms in the series expansion of the natural log of this horrible expression here, and state the values of x for which the expansion is valid. Okay, we'll talk about that at the end. That's something we haven't talked about yet. Looking at this first. To do this, we're going to use the natural log expansion. Here it is. But you can see that the natural log expansion is not going to fit this in here. We need a 1 plus something. We just don't have that here. So first I'm going to need to do some logarithmic manipulation. So we know that the log of a fraction, this divided by this, can be written as the log of this minus the log of this. So I'm going to write the square root of 1 plus 2x, but I'll put it in index form because of what I'm going to do next, minus the natural log of 1 minus 3x. And the next step then, this is okay, I can substitute minus 3x in place of x there, but I need to get rid of this half because that doesn't match this, and bring that half in front instead. Minus the natural log of 1 minus 3x. So now I'm ready to put in the expression 2x here for x and minus 3x here for x. And you could go ahead and plug these in one big expression, but to save having a plus dot 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 halfway through and at the end, I'm going to do these two separately and put them back together at the end. So a half log of 1 plus 2x here in green is equal to a half times the expansion of log of 1 plus 2x, which is the same as this expansion, but with a 2x instead of an x. So I need the first three non-zero, that's going to give me 2x instead of x, minus 2x squared instead of x squared over 2, plus 2x cubed instead of x cubed over 3, and then I would have a minus dot dot dot, but we don't need any more than that. In purple, I'll do the other one. We've got a log of 1 minus 3x, so substituting minus 3x in here for x gives me minus 3x minus 3x squared over 2 plus minus 3x cubed over 3, and you can see for various reasons these brackets here are very important, and then minus dot dot dot, but we don't need any more. So I've got the two expressions here. I can now put them back together, doing the green one minus the purple one. So going back to blue, this equals half of 2x is x minus 4x squared over 2, and half of that is x squared, plus 8x cubed over 3, half of that is 4x cubed over 3, and then we need to subtract the ones in purple, so we've got minus 3x is plus 3x, minus 9 over 2x squared, so that's plus 9 over 2x squared, and then minus 27x cubed over 3, so that is plus 9x cubed. Simplify all of these, gives us 4x, minus x squared plus 9 over 2 is plus 7 over 2x squared, and then we've got 4 over 3 and 9x cubed, which gives us 31 over 3x cubed. So these are the first three non-zero terms, and I could have a plus dot 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 there, and then an approximately equal to sign here. Now the final thing to think about in this question is the values of x for which this expansion is valid, because here we've got a limit on what we can put into this expansion. X must be between minus 1 and 1. So in green, where I've used a 2x instead of an x, that must mean for the green one, minus 1, 2x, 1, which means x actually has to be between half and minus a half. But there's another restriction, and that's the purple one, because here I used minus 3x instead of x. So for the purple one, we had minus 1, minus 3x, 1, and if I divide by minus 3, don't forget to flip your symbols the other way. So you get 1 over 3 is bigger than x, bigger than or equal to minus 1 over 3. And this might look like a bit of a problem, because we've got 3 different expressions for x in terms of the range of values this is valid for. This one here, and this one here. Now this one here isn't really true for this question, because we haven't actually used x at all in our expansion. We've used 2x and minus 3x. So it's this one or this one. But because we've used both, they are both true. They both need to be true at the same time. So if x must be between half and minus a half, and it also must be between a third and minus a third, then the most restrictive range is the one I have to choose. And in this case, minus a third to a third is a smaller range all within this range. So if this is true, this is also true. It must be, because this one is inside this range. In this case then, I just need to take this range as my valid range. However, in a different example, you might have to mix and match. You might need the upper limit of this one and the lower limit of this one, for example. So long as you're choosing the values that make both ranges true. In this case, in blue, my final range is 1/3 x minus 1/3. Okay, our third and final example is e to the x and sine x. Given that the terms in x to the n with n greater than 4 may be neglected, that just means don't worry about any powers bigger than 4. So if we get x power 5, x power 6 or anything, we don't need to worry about those. We can ignore them, and we don't need to write those down. Use the series expansions for e to the x and sine x to show that e to the sine x is approximately this expression here. So we're going to need e to the x and sine x expansions. Here they are. Now to do this, I'm going to look at sine x first and put that expansion into the e to the x expansion. But we need to be careful, because this is really going to help us. Don't forget about this as we do this. So looking at sine x first, sine x is approximately equal to x minus x cubed over 3 factorial, and that's it. Because as soon as I go into the next term, I've got x power 5, which is bigger than I need. I just think ahead a little bit. Will this at any point decrease when I put it into the next stage? And it won't. It will stay as x to the power 5 all the way through to the end. Putting it in here won't affect that, so I know I don't need to include that. I can stop here, which is really good, because if I didn't stop there, it would be a much longer question. Now I'm going to put that expression into the e to the x expansion, because this is approximately equal to this. And this is suitably horrible. It's going to take me a bit of time to work through this, because I need to substitute this whole bracket for x here, here, and in a few more terms up to powers of 4. So we do have a few terms here that we need to write out. So this is equal to 1 plus x, but it's not x anymore. Remember, it's this whole bracket here. So I've got x minus x cubed over 3 factorial, which is a 6. And then plus x squared over 2 factorial, but again, it's not really x squared, it's this whole bracket. And you can see why this is going to be quite a laborious process, because here I will need to square this. I know when I square x cubed, that will be bigger than I need, but when I square x, that will be one of the things that I do need. That's still less than x power 4. So I will need to consider this term, or at least parts of this term. Going on to the next one, this would be following the pattern, x minus x cubed over 6 cubed over 3 factorial. And again, I do need to consider this. Even if some of these terms are bigger than x power 4, I know that x cubed, this bit, will not yet be bigger than power 4, so there are parts of this term that I will need. Continuing on, x minus x cubed over 6 to the power 4 over 4 factorial. And again, at the very least, this one power 4 will still be part of my terms that I need. There's at least one part of this that I will need to consider. But I won't need any more after this, because everything after this is in a power 5 bracket, and I can't get anything less than power 5 out of a power 5 bracket when I'm putting in x and x cubed. So I know for sure everything after this will be too big for this particular example, because anything bigger than 4 is too big. So now I need to pull out all of the bits of these terms that are 4 or less, keep those, and not bother writing or throw away all of the terms that are 5 or more. So let's go for it. Here we've got 1x, x cubed, they're all okay. Here we've got at least one term, x cubed squared, which will be too big. So let me think about what's here. Put this in green. If I square this bracket out, we get x squared minus 2 lots of x to the 4 over 6. So that's x to the 4 over 3. And then we've got x to the 6 over 36. So what I can see here is that I do not need this term. I put a cross through it, it is still there, but I don't need to write it down because anything bigger than power 4 can be neglected. So I've got x squared over 2 factorial, which is 2. So we've got plus x squared over 2. And I've got minus x power 4 over 3 over 2. That's still okay. So I still need that. We've got minus x power 4 over 6. Now I need to consider the terms from this bracket, which are 4 or less. And to do this cubed, I'll just take this expression, which is this squared, and then times another one of these brackets. So I can see, again, straight away, I will need some of these terms, because x squared times x is x cubed, and I can see straight away I won't need some of these terms, because x power 6 times x cubed is way too big. So let's change into yellow here. This one here will give me these 3 times these 2. This one times either of these is too big. I won't bother writing those. This one times either of these is also too big, so I won't bother writing any of those. All I need to consider is this one, and this one times this one is still too big. So there's only one term out of all of this that I need to consider, and that's x squared times x, which is x cubed. And there are other terms in there, but they're all going to be too big. So I already know I don't need them, I won't even bother writing them down. So what we get out of this is x cubed divided by 3 factorial, which is 6. So we've got plus x cubed over 6 from that bracket. And then the same thing. All of this, of which I only really need to consider this term, has come from the cubed bracket. Now I need a power 4 bracket, so it's all of this times another one of these brackets, and obviously all of these terms times either of these two are going to be too big because they're already too big, and they're getting even bigger. This one times this one, power 6, is too big, but x cubed times x power 4 is not too big. So again, the only term here I need is the first one, x power 4, and all of the other terms will be too big. So x power 4 divided by 4 factorial, which is 24. So in blue, the final one I need here is plus x power 4 over 24, and I could write plus dot dot dot, because there are many other terms, but I just don't need to write them down. Final thing to do then is to simplify, and hopefully this gives us the answer as written in the question. We've got a 1 plus x. Here we've got a plus x squared over 2. Then here we've got a minus x cubed over 6 plus x cubed over 6, so they cancel out. Here minus 1 over 6x to the 4 plus x to the 4 over 24 gives us the minus x power 4 over 8. And there we have it, the final answer of the final example of the video. I hope that is enough, although some of these questions do get quite complicated. The basic ideas there I hope is enough for you to have a go at the questions in exercise 7C. and maybe I'll see you in the next video for Taylor's series.